ladies and gentlemen. This is the second lecture of the second series describing the implementation of the RM software for filter design. In this lecture, we will demonstrate the way how synthesis of selective, polynomial, critical monotonic passband amplitude characteristic filters is done within this set of programs. The content of the presentation will follow, introducing the name of the project, introducing the design requirements, synthesis of the transfer function of one representative of the CMAC family, which contains 4 members. So we will spare some time, we'll save some time. Then analysis of the obtained result will be performed, which will be followed by system synthesis, which means passive LC, active RC, active SC, and digital infinite impulse response realization. To start the design, we will activate the RM1 program, and then we will allow blocked content, which is done by the Internet Explorer. And before starting, we will visit the recommended design sequences slide to make our plan of design. So we will first enter the project name, then we will enter the design requirements, then we will proceed with synthesis of transfer function of the CMAC filter, and then we will follow to the system synthesis, which means passive and active or digital synthesis. Now we are starting by inputting the project name, which will be now CMAC polynomial. It is a low-pass filter. These are the explanation of the requirements, and we will input the requirements. 100 kilohertz will be the cutoff frequency. 160 kilohertz will be the, 160 kilohertz will be the upper frequency of the transition band. The maximum passband attenuation will be 3 decibels. The minimum stop band attenuation 40 decibels. This is the asymptotic slope, which will be not necessary for this design, but it is compulsory. This is the group delay, minimum group delay error, which is not necessary for this design, but it is compulsory. And this is the normalization resistance, which will be used for passive synthesis, and it is compulsory. Now we may proceed with the transfer function synthesis. We will go for critical monotone, and first we have to give the order of the filter. The program asks which representative of the CMAC family will be used. We will go for the least square monotonic number 4, and the program says that one will need a 9th order filter to satisfy the requirements, which we accept. for now. Now we may go to the transfer function analysis to see the properties of the solution. Here it is. Insert drawing. And here is the step and the pulse response of the ninth order least square monotonic filter. As you can see, the undershoot here is much smaller, which makes the eye much more open and make it more acceptable for pulse transmission implementation. Here will be shown the frequency characteristic. And again, we will make copies of this for representing the different properties. At the beginning, we will look for the attenuation, which will be enlarged here. Here is the amplitude characteristic 2. We'll come back to it. As you can see that in a very wide interval of the passband, the attenuation is extremely small. As you can see here, this is half of a decibel, and this is 90%. It is 0.2 approximately. Now we will look for the phase characteristic. Here it is. And here at the bottom, we will look for the amplitude and for the group delay characteristic. This is the amplitude characteristic, and this is the group delay characteristic. That is, of course, there are two more, one HTML, one text file, and we will visit the text report in order to conclude whether our filter satisfies the requirements imposed. And here at the bottom you can see is this frequency, which says that the transition region ends at 167 kilohertz, which is 7 kilohertz more than required, which again means that we should restart the project from the beginning with the 10th order filter. That will be not done here. We will proceed now with the synthesis, but generally this is the conclusion which must be followed. Now we go to the synthesis. First, we will go with the passive low pass cascade, low pass. Here are the results. We will look first for the spice file. It's perfect, of course. Here is the group delay. We may look to the passband here. As you can see, it's as flat as possible. Okay, now we will look to the schematic. It is a set of elements, capacitor in the parallel branch, inductor in the series branch, and so on until the end where the load resistor is C. Now we will proceed with the active RC synthesis in the cascade form. Here is the spice file. Of course, it is the same, and we will not pay more attention to that. We'll look now for the schematic. It is 4 second-order cells and 1 first-order cell followed by an inverter. The next step is to go to the parallel RC realization. And here is the spice file. Of course, it is the same. Now we go for the schematic. RC parallel schematic. So there are 4 second-order cells, 1 first-order cell, the summing amplifier, and the details of the summing amplifier, as already mentioned. Then we will go to the switched capacitor realization. We need to supply the sampling frequency and the normalization capacitance, so we can run the program. And here is now the spice solution. Here we choose to simulate the circuit at the half of the cutoff frequency, and accordingly the time step and the simulation time is adjusted. And what we have to look at is the output signal, which is the output of the anti-aliasing filter, which is here in two steps. So this is the output of the second anti-aliasing, and so on. It runs. So since it is time domain simulation, it will run longer. We will not wait for it. Now we may go for the schematic. There are, of course, 4 parallel and 1 second order cells, 1 first order cell, summing, and the scheme of the complete system, including the sample and hold and the anti-aliasing filters. And finally, the digital synthesis asks for sampling frequency, and of course it doesn't produce spice files, so we will look for the CSV file to see the properties. And of course it is the same, so we will go for the attenuation, for the phase, for the gain, and for the group delay characteristic. This will end our search. So since we concluded that our filter will not satisfy the imposed requirement, we have to increase the order of the filter by 1. So what we do is to go back to the start of the design and re-input the design requirements. That would be all for this lecture. Thank you very much for your attention.